Alright, hi and welcome. You're with Tom Harris and we're having a look at the Solid Edge in action. It's a first look webinar. This is a re-recording because of technical difficulties the first time when we actually were live. So we might even be able to fit in a couple of things that we didn't last time due to time constraints. What we'll be having a look at here is a mountain bike. This mountain bike is in Solid Edge, and we've done a whole heap of analysis and things like that, and this is what we'll be doing. Now, if you have a close look at some of the pictures there, you'll notice that the main head stem is actually missing a part, and we're actually also missing some of the components in the suspension linkage and some bolts as well. So we'll be going through part design, simulation, 2D and 3D data reuse, drawing of parts and assemblies, and also assembly design. So these are some of the things that we'll show you over the next short time. Now, with part design, what we're going to do is we're going to design the new head stem. We're going to ensure that the head stem fits around existing components, and then we're going to intelligently edit the part without history. So we'll be looking at synchronous technology, ordered modelling, with the Parasolid engine. So I'll just switch over to Solid Edge, and you can see our mountain bike here at the moment, and I'll just switch our view to a nice basic view, which will be very fast, and it's just a little bit easier to see distinct lines. Now, if you have a look at the head stem, you can see the component that's missing. With Solid Edge, we use configurations to basically control what parts are visible and what parts aren't visible, to just enable getting into those areas very, very quick and easily. Now, what we need to work on is the head stem, which is inside the handlebar assembly. And so I'm just going to edit this stem assembly, and you'll notice that we don't actually have a head stem at the moment. So we're going to create the head stem in place, and it's not a sheet metal component, it's a normal part, and I want this head stem to be aluminium. Okay, so I create that, I'll give it a name, main stem. Yes, I'll overwrite that. And we're now in the component ready to edit, but we can't see any of the other components until I just toggle with a keyboard shortcut Control Q. That makes it very simple. Then what I'm going to do is I'm going to simply start by extruding the yoke or the collar of the bottom ring up to the top nut, and that makes just a very quick and easy starting point. Then I'm just going to very quickly split this component, because I don't actually want all of it. Sorry, not split, rather subtract half of this component, and I want the other half. So I'm gradually getting the regions and the areas that I want to work with. Now, I want to also grab the outer edges of this component. All I have to do is hold down Shift, and then I can very quickly grab it. Using Quick Pick or just straight selection, I can very quickly get exactly the curves and edges that I want to work with. Now, that's all I need for the moment, so I'll just hide the rest of the assembly, and I'll continue on and fill in the remainder of the details that I want to work with. I want those edges on that face, and then I actually want to lock onto this face, and I'll very quickly just draw a straight square. Okay, so we're getting there with our part development. Next, I want to actually make a surface, a smooth surface between those two. Now, I have various options for doing this, and a blue surf is a very rapid option, and you'll notice it's given me a reasonable surface at the moment. However, I might want a little bit more curvature control. So I'm going to make these areas normal to the surface, and just by dragging my handles I can control the shape a little bit more. However, it's still not perfect. You'll notice these transition lines aren't going to the right spots. The top one is, but the rest aren't. So what we can do around that is we can simply go into the advanced control and add additional control vertices. And once I've added them, I apply them, and you can see that's now given me the shape control that I want. So I'll just finish that, and then I'm just going to use a bounded surface to enclose these areas, stitch them together, and what this will do is it will create a nice solid which I can then use and add to the previous solid. So I'm just going to add the new solid onto the previous solid, and I now have the base shape of my component. But you say, rightly so, that I actually want a full circle. Using synchronous technology, all I have to do is delete the cut-off circle, and it recreates a full circle there. Now, I also, if I have a quick look at this, I also need a little bit of clamp gap for these bolts to be able to tighten up and actually clamp onto the headset. So I'm just going to offset that face by 2 millimeters, and that gives us that nice little gap there. Next, I need to somehow create the cutout where the handlebars go. Again, I'm just going to use the subtract command, and you'll notice I can subtract other components in the assembly, and then all I've got to do is very simply delete the faces that are left on the inside of that component. So it's very rapid editing. Now, I also need some bolt holes here, so I'll go and subtract them as well, and quite rightly so, you should point out that the holes created by these are clearance holes, whereas I actually need a thread. Well, we can do what's called recognizing holes. Now you can see it's recognized 2 sets of holes. I don't want the the fork hole to be listed as a hole. I'm quite happy for that to be as it is. But these other holes, I want to change the options. And all I want to do is change them to a threaded hole. Now their current depth is 15.15 millimeters. I'm going to extend the hole depth out to 18 millimeters, and I will have it threaded to 16 millimeters, and that maybe even 17, and that covers the depth that we need to be able to tighten up this hole. And I'll just put a 45-degree half millimeter chamfer on the end, and when I've set that up, I simply accept it, and now I have my nice threaded holes in our part. Now I may also, want to add some rounds or some chamfers. I dare say 5 millimeters is a little bit too big. I was thinking more like sort of a half mil chamfer, and might just need to grab those little end bits as well. And that's a large part of our component done. However, if I have a look, I also need to allow room for a bolt in the end here. Now, we can do that a number of different ways, but Solid Edge has some very powerful tools, and one that I'd like to demonstrate for you in particular, and that is called a redefine. This is an incredibly powerful tool, and it lets me redefine a surface, and as I go I can add additional definition. So I want to redefine this surface, and halfway around that curve I will add another definition curve. Okay, now you can see the redefined surface and the curve that I've got there. Now you'll notice this curve has a little bit of definition, and I can very simply drag those points around to change the shape of my product. However, if I want a little bit more control over the shape of this curve, what I can do is I can actually come in and edit the curve in detail. I'm just going to add 2 more control points there, and then I'll create some relationships between some of the envelope points, and you can see that rather quickly I can develop a much more complex, or whatever kind of shape I want. Looks like I'll let that get a little bit excited there. Oh, I'm on the wrong type of edit mode. There we go. I was on what's called an overall shape edit as opposed to a local shape edit. And that just lets us basically have the control over the exact kind of shape that I want my component to have. And I can fiddle with that as long as I want, but when I'm happy roughly with it, then I just finish and note how the feature updates with my new shape. And then I need to do 2 things. I need to create a split down the middle here, so I can very simply do that just with an ordinary cut. And again, I'll create this cut 2mm wide, and I'll just join it. I'll give it a I don't know, 20mm definition there. That'll cover anything I need, and then I choose which direction I want the cut to go. I want it to go all the way through to the bottom. Lastly, I need to create a hole. Now, you're probably thinking that this hole is a rather strange way of doing this, considering that I want the hole to be on the bolt head, or the bolt, not the bolt head, but the body of the bolt. Using Shift, I can lock down exactly where I want this bolt hole to go, and I'll just put it just very, very roughly, and I'm going to turn on my peers so I can then say I want those 2 to be locked onto center. There we go. However, I haven't specified my hole type yet either. What I want is, this bolt is an M5 bolt. I need a counter bore to suit my M5 bolt, and I don't want a thread on this component of it. The other thing I want to choose is I want my hole definition to be at the top of the hole and the bottom of the counter bore. So I simply choose that option. I'll make sure the counter bore has enough distance to go out the top, and I want the type of hole to be through next. As soon as I've changed that, I simply say which side I want to put the hole, and you'll notice if I hide the remainder of it, it's only put the hole through this side. That is actually what I want. And next I create another hole. This one is just a plain M5 thread. Yep. And I want these to go all the way through. Give it my location. Give it the direction. And then I might just add some rounds. I'll make these ones 1mm, and then I might add a couple more at 1/2 mm, something like that. So I've now completed this part, and let me just show the rest of the model. And so you can see how it fits in. Now, personally I don't like the colour that it's given me, so I'm just going to manually override that back to aluminium. So the next, what we've just seen there, is realistically fast and flexible modelling, and we're now going to go on and simulate this model. We'll virtually test it to ensure that it has the required strength, and if needed we'll make any changes and retest, and we can also generate an analysis report there. So the way we would do this, let's just go back to looking at just the headset and turn on our new part. The way we do this is we come in and we can create a new study. But before we do that, I just want to greatly simplify the job that we're going to do. I'll activate that one, and I'll activate that one, and let me just grab the socket head cap screws as well. Whoops, I'm in the front fork there, wrong spot. Let me just grab the socket head caps. Actually, I won't need to activate them. Next, I just want to grab a copy of this area of the handlebar and this area of the front forks. And all I'm doing is grabbing a copy of the exterior surfaces, because in Solid Edge I have the option of using mixed bodies. So what that means is I can use some solid bodies, and I can also choose to use some surfaces. Now in this case I'm going to use only the two surfaces that I just selected there. Yep. Sorry, I forgot to actually add the surface bodies into my definition. So those are the components that I'm going to use in the definition of my model. Next, I want to apply some loads and constraints. So you can see over here I've got my geometry defined. However, the thickness is incorrect there. This should be 2.5 mil. So fix that up for both of them. And I need to create loads. I can create them two ways. I can create loads on the Pathfinder, or I can create loads directly from the top level menus. And what I want is I actually want it pointing down in the direction of the head stem, and we'll say 120 kilos, which is 1200 newtons. So that's my force defined, fairly simple, fairly quick and easy. I need to define an area that is constrained. All I'm going to do here is choose the bottom edge of the handlebar surface. So now that I've got those two, what I need to do is I actually need to create some joins or connections, and I'm just going to go through and hide some of these solids that I don't need to see, and I'll just grab all of those socket heads. So now I've got only the the components I'm going to use in my model, but I want to create connections like I said. I can create glued connections, which literally does that, but I also need to test the clamping force of the bolts onto these components. So I'm going to use what's called a no penetration connector. And this has an added advantage that I can specify friction in my joint calculation as well. They're quite advanced connectors, and once I accept that, it goes away, analyzes the geometry, and gives me a suggestion of connectors. It's connecting the main stem to copy 5 of the handlebar, it's the main stem to copy 6 of the front forks, and the front of the stem to copy 5 as well. That's good, so I'll just create those connectors. Of course, we need to do two more things. That is, we need to simulate the bolts and we need to mesh it. Simulating the bolts is really quite simple. I'm just going to select the top of my hole. It has a look at the geometry and gives me a suggestion of how to do it. Now I can let it choose, or I can say I definitely want this to be a threaded fastener. This is an M5 bolt, so it has an effective area of 5mm. The bolt diameter and the nut diameter are the area under the bolt and nut heads that will share the load. I'm going to add a 50 Newton preload onto these bolts. So that's the first one created. Next, I'll say all bolts on this plane. You see it detects them very quickly. I'll create one constraint for all of them, and this is an M6 bolt, so I'll just say 6mm and 50 newtons per bolt. So our bolted connections are taken care of as well. Next, we just simply need to mesh. Now you've got quite a number of options here. It has a look at the geometry and suggests a mesh size. This can be good, otherwise you can refine it. I'll go and have a look at the recommended mesh size, or the suggested mesh size, first up. As soon as I accept that, it goes away and uses the FEMAP backend in order to create my mesh. Now this mesh actually looks nice and fine and quite suitable. So I'm actually going to just leave that mesh, and I'm then going to solve. Now, because these models can take a little while to solve, I have a model which I prepared earlier for you, just so that we didn't have to wait for the solve. It takes 5 to 10 minutes for this model to solve. So here's one I prepared earlier. Now, this is the results of the model. You can see that we've got a megapascals worth of stress, 35.9, which is well and truly under the yield. It's telling us exactly where in the model the maximum stress is, and if I rotate around, I can see that it's around the bottom edge, which, to be honest, makes sense because you've got a lot of force pushing down on here. It's going to try and rotate this part around, and that rotation is trying to open up this bolt area, hence why it is also receiving very high stress. Now, if we want to get an idea of how the stress is actually flowing through this part, we can simply use, there's a number of tools, but one that I personally like is the ISO contour. And you can see how it creates a different sheet for each level of stress, and it lets you very, very quickly identify the areas of concern, and it basically leaves the rest completely see-through. That's one nice option. I can also have the same thing but in a dynamic form, and as I move the stress up and down, you can see the stress contours moving as well. So I'll just set that back to all results. As you can see, I can add maximum, minimum markers, all those kind of things. I can save my different display types. Another one that's very handy for getting an idea or a visualization is what's basically a criteria plot, but it's also broken down into broken down with transparency. Now, why it's a criteria plot is I can very, very easily set my criteria. For example, I might only want to see stress above 25 megapascals, and I'll set an underflow color of white, and everything else shows up only what is above 25 and below 36. I might drop that just because it doesn't show very much at this point. Might drop that to 10. So gives you an idea of how easy it is to visualize these results. Now, we don't have to stick with just stress, and we don't have to stick with just standard von Mises. I can also have a look at factor of safety plots. And hang on, let me go back to contour with full color bar. That will give me a lot better idea. Actually, because this is factor of safety, I'll change it to a user-defined from 0.5 to 5. And this time I'll say anything over 5 can be white. So as you can see, basically everything is well and truly over a safety factor of 5. If we crank that up to 25, we're starting to get some visibility. So this model is actually quite a safe model. Next, we'll just go and have a look at displacement, because obviously the displacement of this component is quite critical as well. Let me just say all results. And here you can see that I have a maximum displacement of 0.9 millimeters, which is actually relatively high. So how is it getting this displaced? And you can also see here that most of the display is pretty much the same color. So let's have a quick look and just animate the model. And you can see the whole model is moving up and down. So what is actually happening here is the entire stem is sliding down the handlebar in order to finally get enough clamp force and enough friction on the stem in order to grip. So what we may want to do, and I did this earlier again so we don't have to stop and wait, we may want to simply increase the clamp force stress, or the clamp force. And you'll notice now that we're down to about 0.28 millimeters, and most of that is at the end. So we're starting to look at the actual flex of this component. Note, the overall stress hasn't changed much at all. So by quickly doing a couple of iterations, we've been able to identify what an issue was and fix it. And how do we report this? Well, I can very simply click Create Report. Yes, I want to create the report, and I get to specify what it is, who I am, Tom Harris. Oops, helps if I spell my own name correctly. Edge PLM, and this is part. This is the handlebar stem. It looks safe. So I can give it a location. I can choose what format I want my report in. I'll choose Word, and I'll go and create my report. It will then open up that report because I chose to create it in Word. It will open up or create the report in Word and populate it with the introductions and conclusions that I specified. Gives you the model information, the study information, so that someone looking at this can go back and reanalyze it. All of the material properties, if you override any properties, it shows you them. The forces, the constraints, connections, all of the mesh information, and lastly, the actual results in both stress and displacement and factor of safety. If you've done optimization on this model, which I won't go into at this stage for time's sake, it will give you the reports of that, and lastly, it gives you the conclusion. So we've got quite a bit there. The reason we highlight simulation is because it reduces physical prototypes. It leverages an industry standard FEMAP and NX Nastran, and it is very highly scalable for more advanced needs if you need to do more things like that. So you can see that Solid Edge has fully integrated design analysis. Next, we'll be having a look at 2D and 3D data reuse. We'll be opening a 3D part created by another designer, and we'll be editing that geometry to ensure it fits into an assembly. Then, we won't actually create a 3D part from a 2D drawing, but instead we'll use two different components, a step file and a DWG file, and we'll bring them together and show you how that can make a fully editable part in Solid Edge. Because, let's face it, a lot of us have legacy data that we still need to be able to reuse. So I'm just going to close down that one, and let me hide my simulation, and I'll go back to looking at the rest of the model, the rest of our assembly. Now, what we've got here is we're completely missing a component in this model. So, first of all, we're going to import a component. So all we have to do is click on Open, and for ease of use, I'll select the top link step file. We've got various options while we bring these files in. Most of the time you won't need many of the options, but they are there if you do need them. So once you've imported the part, which it's just doing at the moment, you can see I've got a fairly normal part to work with. Whenever you import a model, Solid Edge has tools to optimize these imported parts and basically give you a fully editable geometry. Sometimes other programs don't use the same trimming precision, so that step just goes through and makes the model a lot more usable in Solid Edge. Now, there are lots of things that you can do with a model like this. For example, I might just simply select a hole and I might choose to modify it. Now at the moment, it's not letting me modify that, and you can see I can have a look at the solution manager, or in this case, I know it's locked to the Z axis, so I can simply say unlock that, and I can move this around as desired. I might choose to, change the width, but notice this is a free model at the moment. There's no constraints. So if I want to change the overall width, I probably should select both faces. And you'll notice I can now change the width. Now, if that's not the desired result you're after, you can do all sorts of things with Solid Edge. You have a raft of different options in order to make the change behave as desired. And you see that's just one of them. But what we really want to do is we want to use a DWG that came with this model to give us a completely nice editable component. So I'm just going to save that top link, and then I'm going to open the DWG file that came with this model. So I just go open my DWG file. Again, I've got a whole heap of options. I won't bore you with them at this stage. And what I want to do, first thing I should do is check what scale it is, because you never know what scale people write models out at. Oops. And the dimensions match. So this is a one-to-one drawing. So I want to create 3D, but instead of adding it to a new file, I want to add this drawing to an existing file. And I'll just go in and browse for my file, which is the new top link that I just created. And I'll just type in top. There we go. And I've got various options, whether I'm in first angle, third angle, and whether to include dimensions. Okay, that's all I need. This lets me set the view scale if it's not one-to-one. And then I simply select my views. Probably don't need that one, but I'll select it anyway. And then I'll simply finish. And what it will do as you can see, is it adds all of that geometry onto my model. Now, what I need to do now is I need to move this geometry, or these sketches I should say, so that they line up with our actual model. And it's quite a simple process, and you see how I can use the geometry of both the sketch and the model to line them up, and then all I need to do is I right click and I attach the PMI dimensions to my model. If I hide those sketches now, you'll see that I've still got dimensions, and these dimensions are still attached to my model. For example, I might want that to be 67 millimeters, and it makes a change. So you see, I've got full control over this model. I've got an offset here of 1 millimeter. Now, I can choose which face actually moves if I change this offset. 2 millimeters, and it moves that face 1 millimeter. Or I can lock that offset. If I lock that offset and I go to change this dimension now, let's just say 68, you'll notice what happens is it will actually have to move not just the first face that the 68 is attached to, but also the face behind it that is set by that offset. So you've got a large amount of control just simply by having these dimensions. You know, I can go through, I can lock dimensions as needed. I don't want any of them to change, so I'm just locking those dimensions. Now, I may need to, make some fairly drastic changes, and one thing that isn't on here, it's just assumed, is that the width across this section is the same as this 6.5 millimeters there. There's no actual control over the geometry here. So all I need to do is I just need to say I want to create an offset dimension. Use quick pick to select the back face, and what do you know, it's not actually 6.5, which it should be. So I'm just going to change that back to being 6.5 as it should have been and accept it. And now what you'll notice is, let's just say I want to rotate that face. Notice that it's staying 6.5 millimeters thick now. So it gives you a lot of power and a lot of control. What happens because I've locked this 6.5 millimeters? Again, I want to make this a bit thinner, overall thinner. So I simply pick up my face and I can make it a bit thinner. But what happens when I get to this point here? It won't actually let me select this point on the end here, and there's a good reason for that. Okay, the reason is because I actually have some radiuses here, and it doesn't know what to do with those radiuses when I reach that point. So all I'm going to do is I'm simply going to delete those radiuses, because I want this to be a completely flat-sided component. And then I'm just going to select that edge. I'm going to zoom up a little bit here so I can select the correct vertex nice and easily. And if, in cases like this, it's getting in the way, I simply hit Control-Shift-D and it lets me create or select my vertices without the preview. So I've got various tools in order to make sure I can create just the edit I want to create. Now I might want to change the width of this. I can do it various ways. You've already seen me use a dimension, or I can just grab the entire side and, for example, push it in or out. And I might want to bring this in by, I don't know, 5mm. We'll see how that goes. So let me just save that component, and I now want to bring my top link into this assembly and make it fit. But before we do that, we'll just go back and have a look. So we've opened a 3D part created by another designer. We've extracted the information from a 2D drawing and put that into the 3D document, and we've been able to edit the component quite simply and effectively. So you can reuse your legacy 3D data. Modifications are direct without needing to understand the history of the component, and your legacy data is converted, not lost. This basically means you've got an easy transition from 2D to 3D. Now, before we continue actually, we probably should go and create a drawing of that component. So I'll open the top link again, and we'll just create a drawing of this component. It's quite simple. You just come into the drawing environment. It has a look at the views, and you can simply place your views very quickly and easily then. And if you want, things shaded, you can just do that as well. Repositioning, you don't need to worry about keeping your views aligned. Solid Edge takes care of that automatically. Now, we've also already gone in and created the dimensions on this drawing. We brought them in from 2D, but we can't see them. All we need to do is simply retrieve the dimensions that we already have for this component. And at times you may need to reposition some of those dimensions, but most of the time they'll come in very cleanly and ready for you to simply use them or display them. But the next thing to do is we obviously need center lines and annotations like that. We've got a very nice simple tool to create your automatic center lines. Now, if you do want to do things like dimension the component in 3D, we can also do that. We've got all of the tools to enable you to create quite complete dimensioning in the 3D environment. All of those tools are there for you and simple to display. Creating parts lists, obviously, this is only a single part. We can just create a list from, for example, this view, and I can have set up different types of parts lists depending on what I'm creating a list for. This is a parts list for simply a part. At the moment I don't have any material assigned, so it's got a 0 mass, but that's quite simple to fix. I can just double click on it, see no material assigned, and I want to assign this a 6060T5, apply that to the model, and you'll notice that the mass, as soon as I update it, it's all there. If I want, I can display center of mass and center of volume. In this case, they're at the same position, and I can choose to update these properties on save. So now that I've got my physical properties in there, it's going to tell me that it's out of date and I need to update. And notice it's now given me both the mass and the material. Thickness is there for a sheet metal component, so in this case I don't actually want the thickness column. All of these are completely customizable. I can move them around and change them as desired, and if I want to format the columns, it is really quite simple. I just drag the column lengths around. If I need to actually go in and create a different name, I am allowed to do overrides and all of that kind of stuff. Now, it also gives me a balloon on my drawing. If I don't want that, I can simply remove it, and a balloon alignment list. So creating drawings is really a very simple process in Solid Edge. If you have surface texture or feature control frames, I'll just show you, for example, a datum frame. I might put a datum frame in here, and it's called A. Now, I'll move this drawing up so I've got a little bit more room to work with. I might desire for this bottom frame to be, for example, parallel to the bottom, parallel to A, sorry, parallel to the top. Within 0.05 degrees. So I can create, my feature control frames. However, what happens if somebody decides to call this, for example, datum C instead of A? Well, because Solid Edge can link the datum numbers, it automatically updates, and you don't have to chase that kind of alteration through your geometry. Now, can you add additional geometry other than what was already specified in the model? You certainly can, and you basically just do it as desired. I'm not sure that there's really anything else I need to dimension in this model, maybe just dimension in there. If I want to add prefixes and suffixes, I might want to add a typical onto this dimension. I can do all of that kind of thing as well. And I can also add my, my basic dimension callouts. I can have nominal, I can choose to make it an inspection dimension. I can add unit tolerances or alpha tolerances. I can add class fits, limits. Basically all of the different options are in there as well. So we can add all of the annotations as desired. The view creation is automatic, and the views are linked back to the model, as are any dimensions that you create, and it's all clear and accurate to the standard that you choose. So we give you production proven 2D drafting. We'll now move on to the assembly design, which I nearly started earlier, and we'll show you how you can assemble components very efficiently. You can add standard fasteners, you can check for interferences and other conditions like that. Alright, so just save that draft as top link, that's fine. So we're now ready to bring in our top link, our revised top link. All I have to do is type in the name and it takes me to it very quickly. However, I don't have to just drag it in. I can get the orientation roughly right in the preview window before I drag it in. And then it allows me to position it just by simply selecting the different areas or planes and just come in and have a closer look here. Just want to line them up as well. And so now my component is positioned. However, is it the right size? And you can see that it's not, because I've got a little bit of a gap in here. And let's just find out how much of a gap it is. I can, choose between faces if I want. However, I'm not just limited to faces. I can also say, what's the minimum distance between this solid and that solid? And you can see there's 5 millimeters there. Let's have a look at surfaces. I'll go between that surface and that plane. And there's 4 millimeters between there. So this component actually needs to increase in width by 4 millimeters. So I'll just go in and edit just by double clicking on it, and I'll select this side of the component just with a simple window select, and I'll add 4mm, 58mm. That should become, and very quickly it's now 58mm. Control Q shows me the component again, and I can see that that is now the right width component to match up with the assembly. So we've very quickly been able to modify these components, or bring this component in, which was a 2D component, and modify it. What do we want to do next though? Well, if we have a look, we can see that very closely. You have to be watching carefully. You can see that there's actually interference between these two components. Well, let's just have a good close look at that, and I want to check interference between any of these three components. All I have to do is use the check interference command, and as you can see, it highlights the interference that exists between these components, and basically where we suspected is the only area of concern. So what do we do about that? Well, realistically, we can do, well, we've got to basically lengthen this top link again. So we'll come in, and this time I'm going to select the whole of that bottom area, and I'll just simply increase by 10mm. That should be enough to get us clear. So that's now 90mm instead of 80mm. Hit Alt-U to update the assembly, and you can see that it's now given us the new view, and you can see an air gap running down there between the two components. So that's pretty good, but realistically it's still a very close fit, and this bike is actually not at the limits of travel. If we have a look in our variables, you'll see that the wheel travel is already 50mm up. So if we drop the wheel travel to the bottom, you'll notice that linkage moved further down as well, and it's now crashing again. So increasing the top link was good, but it didn't completely solve our problem. We'll probably have to edit this rocker as well. And what I want to do is I just simply want to move this part of the component a little bit further out, probably again another 10mm further out along this line. So how do we do that? Well, we simply select the hole and select the direction we want to move it, and notice that the live rules are maintaining the intent of our model. So we've moved that out. We may even want to move this out with it, or indeed not move it because it's still actually centered, but we may want to decrease that radius. We'll decrease that to 17. And that gives us our nice clean lines that we were still after, and it pushes the linkage area away from our frame enough so that we're no longer clashing and crashing. So we better check the other limits of our travel. Just bring up the variable table. This has the up to 150mm of travel, and you might notice that all of the chain, the derailleur, and the cables have to update during this edit as well. So it's quite an extensive edit, and you can see that this at full compression extends it all out, and we're still right. So we'll just bring it back to normal ride position, which is 2 inches compression, and we're pretty much right. So we've just completed a series of edits within the context of the assembly. We've worked very rapidly to make these components fit and not crash and detect interferences. So, oh, sorry, we haven't added the standard components yet, standard fasteners. At the back here, you'll note that we've got a bolt missing for the top of the shock. Solid Edge comes with some very nice tools. So we'll place a fastener system from the top hole, not all holes on face, just the top hole, all the way down to the bottom hole. It brings up a list of components that I can choose from. I'll go just an M8 grade B hex head bolt as the top as the bolt. I don't want any washers or anything on the top stack. Bottom stack, I want a washer, just a standard M8 washer, and I want a nut, and I'll have a prevailing torque hex nut. Add that as well, and they're in the right order. So then all I have to do is say OK, and it generates the fasteners, places them into the assembly. Okay, so very quickly, I can place my components in. There's my fastener system there. I can edit that if I want to, for example, change my fastener system so that it's instead of a standard screw, screw on top, I might want a hex head fastener instead, and that changes it out and gives me my hex head fastener. So just to review, we can assemble things very, very quickly, ensuring fit and function. We can save time by editing the parts in the context of the assembly, and we can reduce effort putting bolts, nuts, screws, things like that in with fastener libraries and standard components. So we've got the tools for complete digital prototyping. Next, we need to have a look at creating your assembly drawings, and creating things like parts lists with balloons, and even exporting drawings as 3D PDFs. So we've got our component. We probably should save it at this point, and we'll then go and create our drawing. So we create the drawing view the same as we do with any part, and I'll just go in and make sure I've got the view I want, and then I'll add additional view types. Now if I drag this over a little bit, you'll be able to see I've already got a shaded view. What I'll do is I'll have shading without the edges. It's chosen to make it a bit smaller. I can override that choice if I want. However, to be honest, it's probably quite a reasonable size considering the amount of detail that will be in these views. So it's just going to go away and generate those views. And we can move them around as desired, position them however we need to position them, and notice all of the alignment is maintained. Just makes it a lot easier. Now we have all of our standard view scales, but we can also do custom view scales if desired. Oops, that was a little bit too big. I meant 07. So we can do all of those things as well. Now, another thing we can do is we can generate a parts list from these very simply. This time, instead of a part, I'll actually choose a top assembly list. I'm just going to place this in the top corner, and it goes and generates auto balloons. Now, if you don't like where they're positioned, you want them a bit closer or something like that, you can simply drag them and reposition them. Now, another thing that you'll notice is the default is for the item or the balloons to come with both the item number and the item count. I now want to change all of these balloons. While I could have changed it before I placed the parts list, I wanted to show you another tool, and that is Smart Select. And this is a tool which will enable you to select all of an element type or layer or color, depending on what you select first. And then you get to change all of those items at once very, very simply. So I've now removed item count from my list, and it's updated all over the component, with all the balloons, I should say. The next thing I want to do, I want to create a broken out section view. Now, it's quite a unique type of view in that I can define what I want to cut. I'm just going to do this very roughly. I can define what I want to cut on one view. I can define the depth of the cut on another view. And lastly, I can define which view to actually perform the cutout onto as a third view. And what you'll see, I'll have to zoom in a little bit, and these views are created with fairly coarse shading as a default. I'll also update the shading just so it becomes a little bit smoother. Now you'll see it gives me a list of any annotation changes. I just want to go into the properties to update my shading, and instead of 150 I'll take it up to something like 300 dpi. Just update the view again. And you can see that it's created that cut through all of the components. Now I may not want all of the components actually cut. I may only want some of them cut. I definitely want the frame cut. I want parts of the chain cut, and in the where is it, the Fox shock, let me just find it, it's in the rear linkage. See, the bearing and a whole heap of other components in there are also cut. Now I want all but the actual shock to be cut, so I just simply select those two and say I don't want to section those two components. Say OK, update my view again, and it updates with just the components I want cut and the remainder not. So you've got various very powerful tools for creating your different views. We also have a very nice tool. I'll just create a new sheet, and this one I'll also make it an A3 sheet. I'll place another view. Now we give you the option, I'll create a view of the front forks. We give you the option of selecting another assembly out of the full list. In this case I'll just select that view as my primary, and I'll create another 3 views and place them as well. And so it enables you to go through your entire assembly quite quickly and document all of the various components. I want a sub-assembly, but I also want to just double check. There we go. I've already set that up to not use the item count in the ballooning. Move these over to give me a nice bit of room, and it's now got my components. I can pick off, critical dimensions. You'll notice it's still using the typical that I had from before. I've just got to deselect that if I want to, and I can go through and add all the various limits that I might need to. And I might add a comment on this one. Max travel. Don't want that. That doesn't need to be to all of the decimal places, and I can add detail as I go through and document my assembly. So we have a raft of different tools available for assembly drawing. Now, I forgot to do the PDF. I'll just you'll notice in our save as options, we can save to a PDF as a 2D document, or if I just switch back to my 3D document, you'll notice that save as translated, you'll notice that I can save as a 3D PDF document as well. And we can just have a quick look at a 3D PDF for you. And these, of course, give you all the tools appropriate to a 3D PDF file. You can do all of your rotation, you can select different components, you can expand the tree and highlight different bits, turn different bits on or off, really whatever you choose to do. Now I might turn off the rear linkage, check the derailleur, all of those kind of operations that 3D PDFs give you. I do believe it also gives you the option to actually create measurements. That would be in tools. No, it wouldn't. Analysis. There it is. Your measuring tool. And I'll select a snap to a circle, because there are an awful lot of different circles on these rims. See, so we've got a dimension to the centres of 1.17. So you've got various tools available in just simply a 3D PDF for communicating the extent of your design. Now we also have things like a solid edge viewer, which will allow you to distribute and view files natively, or things like ExpressRoute, which are specific collaboration tools for you to be able to use with your customers. So we've got all of the collaboration options in there. We've demonstrated automatic parts lists and ballooning, advanced views, and collaboration options, again showing you the production proven 2D drafting. So all up, it comes down to accelerated design in both part and assembly, drafting with both part and assembly, just to be able to give you faster end product, and simulation and data reuse, again faster revisions, more repeat business, better use and reuse, so that you can give your customers better competitive pricing. What it all comes down to is Solid Edge has a lot of tools for you. So we're now at the question area. If you have any questions, you can review the webinar on the Edge PLM YouTube channel, or you can ring our Australian support hotline on 1300 883 653. The questions were answered in the original recording. So thank you very much for watching.